Right, hello, this is yet another exciting time of physics, Unit 2, and today we're going to be doing all about springs. Now, if you've watched some of my other videos, I have mentioned Hooke's Law, which is exactly what we're going to start with. Now, what is Hooke's Law? Before I write anything on the board, I'm going to explain exactly how Hooke's Law is stated. Obviously not in this book right here. But Hooke's Law says that the force applied to a wire is proportional to the extension from its unstretched length, which is just delta L. So, how do we put this into a formula? Well, there's one thing is proportional to another. Force is proportional to delta L. So that tells us that there's got to be a constant of proportionality. And physicists call this K, which in English terms is stiffness constant, which in real English terms means like how a gradient, for example, how stiff it is. So that means F equals K times delta L, and K being the constant of proportionality. And that's great for a single wire, like this. The dashed is the roof there, and the line is meant to be a single wire. And that is the F is, a thing to mention is F is also basically another way of saying W. Because the only force you're going to apply to a spring in the case of AS is a weight. Now the weight is it's a force, it's measured in newtons, and that is the force applied to the spring. Now, you don't just have one spring in a couple of occasions, you can have more than one. Let's give it this, for example. So these are two springs, and we have a bar here and a weight pulling it down, W. If the weight is in mass, you need to times by the acceleration due to gravity, which is given on your formula sheet of about 9.81, and the bar holds the weight over the two springs. Let's call these, so we can divide it up, spring P and spring Q. Okay, so we've got two springs there, and we want to know right. No, actually, before I do a question through, I'll explain how the formulas and what you would use to just generally work things out, and I want to prove it to you. So, you know F equals K times delta L. That's correct. These two springs will have different constants, generally. So that means K, we'll give one KP and KQ. And if the spring constant is different, then the force, or if we're using the same force, then the extension is going to be different. But if we assume they're the same, as they generally are, we can use F. So basically, two lots of F is W, but we're going to write it as F plus F. So W equals Fp, which is the force on P of the weight, plus the force on Q of the weight. Now, as we said, F equals K times delta L. Delta L is just a thing, so we can't change that. So W equals KP times delta L, bracket that, plus KQ times delta L. And you can rearrange this to find the, say we've got two delta L, and the two constants are 15 Newton meters, and our weight is 30 Newton meters, and we want to know the extension. Sorry, I just had to work that out in my head then to make sure this would work out right. So we know the two, let's rewrite that in. So we've got W, as we said, 30 newtons equals Kp, which is 15 Newton meter, times delta L, which we are unaware of, plus 15 Newton meter, Newton meter times delta L. Now we assume, because these have got the same spring constant, generally, which they do, we wouldn't try to trick you like that, I haven't seen one. We can just use simple rearranging techniques, so 30 n over, now we won't do it over 15 because there's 2 delta L's to consider. So we times the 15 by 2 so we can work out 1 delta L. So 15 Newton meters times 2 over 30 gets you 1 meter. So if this is the delta L, L up here, then delta L down here will be equal to 1 meter. Now, you've got to be careful. Now, the 1 meter isn't how long it is now, it's how much it's extended by to get its new length. How much it's extended by to get its new length. So you add that on to the previous length to get your new length. Because the old length just doesn't disappear, you keep it. And that's the same for working out, if we're working out the spring constant, assuming they're the same. So let's assume they're the same, and I rubbed that out into F equals K times delta L. Now let's do this equation if we were considering 2 springs. However, this time not just 2 springs they were in series, parallel even, because I was going on to it here. So you got springs in parallel, which we've just done. And now the other type of 2 springs we can have is aligned together, so they are in series. Sorry about that. So I'm just going to draw one big thing here and then break it up into 2 springs. Top half is P, top half, and bottom half is Q. And as before, we've got a W. And now T is equal to W. And this, because it's in the form of one line, we can still use the formula F equals K times delta L. Now the delta L is going to be the same for both because they are aligned together, so they get pulled by the same amount. Whereas in a parallel, that might not have been the case. If one had a high spring constant, it would pull to the left or pull to the right. But this, they could have different spring constants, but have the same extension. That's quite magical. So, I know I'm not on drugs, by the way. I do not touch that. It's just a bit weird, that's all. So, F equals K times delta L. Now, if we know delta L is the same, the only thing that can be different is K. So, we have to do something called the effective spring constant. Now, I'm going to do this effective spring constant for this and show you the effective spring constant for the parallel after this, just so you don't get confused. Just so I can show you why you're going to need to use it, because I don't think you would have done in the other occasion. So, the effective spring constant is a spring constant of all of this. So the effective spring constant is 1 over K equals 1 over Kp plus 1 over Kq. And this K here is what you're going to use, because T is equal to W, so equals F. So as F equals W, we'll just use F, okay? So F equals K times delta L. Now 1 over K is not K. I know it sounds stupid, but some people make that mistake. It's K on the bottom that you need to worry about, and that will give you the K over there. And then you times that by delta L. Now, that is the effective spring constant there. Delta L, as I said, is going to be the same for both springs. So, that is going to be the overall force that's acting on the two springs. And you can rearrange this to get F over K equals delta L, or W over K equals delta L. And some questions might require you to ask, well, we need there's a 4 Newton force added and it creates a 20 metre extension. How much do you need to create another 30 metre extension? So what you would do in that case is you assume you'd take your mind off the now if you've given the spring constant, then you can take your mind off what they've given you. But if they haven't, you need to work it out by how we said before about the effective spring constant. Well, let's assume they have. So if they have given you the spring constant, then, and they've said 40 metres equals 4 newtons equals 20 metres, then you work out the amount needed for 50 metres, because it's 30 plus 20, and then you've got that force you need, say 8 newtons creates 50 metres of extension. Then you take that away from the 4 newtons and it gives you the answer you need to extend it even more. You've got to remember, you might catch you out on that one. So, I said before, I'm just going to go over the effective spring constant for the one in series. Sorry, put that again. So, as we said before, in parallel. So as we said before, we've got the 2 springs here, and then the bar, and then your weight there. So hopefully we should have got before. I'll just write the formula down. So K P times delta L plus KQ times delta L. If you're unsure of how we got that, you can rewind this video and see how we got that. But that's what it is. Okay, so the effective spring constant, and now they're both K, if you can't quite see that. I know it looks a bit like an F, but never mind. So that's a Z, whatever you want to call it. It's going to be a K. But as long as you can understand the physics, laugh at me, I don't care. Okay, so you've got 2 K's there. And now the effective spring constant is the combination of all of them. Now, as we said before, the effective spring constant in series is, imagine it's as one spring, whereas the effective spring constant combines the two constants. Sorry. So you just basically add the constant. So the effective spring constant is K equals Kp plus Kq. That's the effective constant. That is basically what you need to know. And you can put that into the other formula to get force, extension, whatever you need. That is basically the gist of what we tried to get across there. Hopefully this video has helped you for AQA. What we're going to do now is going to sign off. That is springs done and dusted. Hope you enjoyed it. I did too. We're going to go on to density in our next video, and if you're watching this the right way around, we're going on to optics, and then we'll go back all the way to, if you're watching this the way I did it, all the way back to scalars and vectors. So we've not got that long to go. Now, see you in the next video.